Hello, welcome to Chapter 5, Analyzing and Representing the Relationship between Categorical Variables. In Chapter 4, we saw how to analyze the relationship between two variables when they are numerical. We used a graph, the scatter plot, and numerical analysis with the correlation coefficient, the coefficient of determination, and the regression line. In this Chapter 5, we work with categorical variables. Instead of a graph, we will use a contingency table, and the numerical analysis will be done with probabilities. That's why in this chapter we will also cover some basic concepts on probability. Probabilities will be paramount from now to the end of the course because the block about inferential statistics, which begins after this chapter, is based in probability distributions. In exercise 1, we cover the two devices that we use to analyze the relationship between two categorical variables, a contingency table and probabilities. A contingency table or two-way table is something like this. In a way, this is the equivalent of a scatter plot. Here we have a sort of x-axis, and along it we have the different values of a variable. In this case, the variable program. And here we have a sort of y-axis, and along it the different values of another variable, in this case the variable gender. An individual located here has this value for the variable program and this other value for the variable gender. The main difference is that when both variables are numerical, it's very unusual to have repetitions, because even if two individuals have the same value of x, it's unlikely that they also share the same value of y. When the variables are categorical, it happens the opposite. We have many repetitions. So here we see not only one individual, but all the individuals that are female and study infotech. We always assume that the values of each variable are mutually exclusive. This means that they cannot happen together. That's to say, a student cannot be enrolled in two of these programs simultaneously, and the same applies to gender. With the information contained in this table, we can answer the question: is there any relationship between gender and program, or are these variables independent? In this context, independent means no relationship, and is the opposite of associated. We asked and solved the same question for numerical variables. Remember when we wondered, is there any relationship between age and visibility distance? And the answer was yes, there is a strong relationship. The older the driver, the shorter the visibility distance. We also wondered, is there any relationship between the mother's weight and the baby's weight? Then the answer was no, there is no relationship. The weight of the newborn is independent of the mother's weight. Here we do something similar by means of probabilities. So it's time to introduce the four types of probabilities that we will work with. The first type is the marginal or total probability. What you see here in italic is a non-official hint that I give on how to obtain such probability. An example of question about this type of probability would be: what's the probability that a randomly selected student is female? Here you may think it depends on the program. There is one probability in art science, there is another in business economy, and so on. This is true, but we call this a total probability because the question is, if we consider all the programs together, in other words, if we forget about the variable program, if we look at all the students, what's the probability of randomly picking a woman? We denote and answer this question in this way. There are 12,000 students and 6,198 of them are female. So this is the probability and this is the decimal approximation. I say that we work only with one variable, gender. The other variable, program, is disregarded. Our total, that's to say the denominator of our fraction, is the grand total, that's to say the total in the whole table. In these exercises, it's common that you are expected to write the question in mathematical notation. This P parenthesis female means the probability of female. it's not P times female. In mathematics, the parentheses also mean a function evaluated in a value. We see this in expressions like f of x equals whatever, or the square root of 4. This is not the square root times 4. It's the function square root evaluated in the number 4. Here another example. What's the probability that a randomly selected student is studying art science? Here we are disregarding gender. We work only with program. We denote the question this way, and this is the answer. Among the 12,000 students, 8,994 study art science. Some people say that we call this a marginal probability because we can find the solution in the margins of the table. The second type of probability is commonly called joint. It's the probability of two events happening together. Example, what's the probability that a randomly selected student is female and studies art science? Here we still work with all the students, that's why I say that our total is still the grand total, but now we involve two variables, gender and program. We want the student to be female and to be in art sciences. This is the question in mathematical notation, and this is the answer. Among the 12,000 students, only 4,660 are female and enrolled in art sciences. Usually this type of probability uses the word and, but don't rely on that because you can also find the same question phrased without the and. For example, what's the probability of selecting a female art student? It's the same question with no and. The third type of probability is the most important when it comes to analyzing the relationship between categorical variables. We call it conditional probability. Here an example. What's the probability that a randomly selected female student is studying art science? In this question, the student is female for sure. This is guaranteed. Males are excluded here. And the question is, among women, what's the probability of randomly picking one who studies art sciences? This is the question in mathematical notation, and this is the answer. There are 6,198 women, and 4,660 of them study art sciences. This is read the probability of art sciences given female. Here I am using a kind of color code. This female is in bold, same as the denominator, and this art science is regular, same as the numerator. This expression looks almost the same as the fraction. Just this bar, which means given, is perfectly vertical. Another example. What's the probability that a randomly selected culinary arts student is a male? This is the probability of male given culinary arts, because we are focusing only in those who study culinary arts. There are 177 of them, among whom only 94 are men. At the end of this exercise, we will see how a conditional probability is used to analyze the relationship between categorical variables. Notice that when working with probabilities, usually we want the decimal approximations because they are easier to compare than fractions with different denominators. There is an equation that links joint, marginal, and conditional probabilities. The joint probability of A and B equals the marginal probability of A times the conditional probability of B given A. You can double check this with the numbers that we got above. The third decimal may not be the same because of the rounding. The last type of probability that we study is commonly called combined probability. What's the probability that a randomly selected student is female or studies art science? Here we involve both variables, program and gender, but we don't need both conditions to be true simultaneously, like in the joint probability. Here it's enough with being female or with studying art sciences. If both things are true, that's also okay. We denote the question this way, and the answer is the probability of being female plus the probability of studying art sciences. The common mistake is finishing here. This would be a mistake because when we counted these females and these students in art sciences, some individuals were counted twice. Which individuals? The 4,660 who were both females and students of art sciences. Therefore, we still have to discount them. That's how we get the combined probability. Remember, the most common error here is not discounting those who are double counted. This is the formula that links combined, marginal, and joint probabilities. The combined probability equals the marginal probability of one plus the marginal probability of the other minus the joint probability of both. If we know for sure that the events are mutually exclusive, then the joint probability is 0, and then the combined probability is simply the addition of the marginal probabilities. To finish this exercise, let's explain how the conditional probability is used to analyze the possible relationship between two variables. Two events are said to be probabilistically independent when the occurrence of one does not affect the probability of occurrence of the other. The following three equations are equivalent. Any of them can be used to prove that A and B are independent. The first equation is probably the easiest to understand. Here we compare a total probability to a conditional probability. This says that the probability of A when we have the guarantee that B occurred is the same as when we don't have the guarantee. So the guarantee of B does not change anything. This second equation says that the probability of A when we have the guarantee that B occurred is the same as when we have the guarantee that B did not occur. The superscript C means complement, the negation of B. So again, the occurrence or not occurrence of B does not change anything. The third equation is the hardest to explain or to interpret. Usually, we don't use it to prove independence, but to calculate joint probabilities when we already know that the events are independent. If the events are independent, the joint probability is simply the product of both marginal probabilities. We'll see this in the second part of this class. Let's go back now to our contingency table and the variables gender and program. We are going to apply these concepts of independence to the values of the two variables. For example, question E. Is business economy independent of gender? In a question like this, you want to use the second equation to test independence because it's easier to understand what you are doing. You remember that the purpose of a regression line was expressing the y as a function of the different values of the x. Here we do something similar. We want to get the probability of certain y as a function of the different given values of x. In particular, we are going to study the probability of business economy as a function of gender. We must get the probability of business economy given female and the probability of business economy given male. If these two probabilities are the same, the gender does not make any difference and business economy is independent of gender. If they are not the same, one gender is more likely than the other to study business economy, and then this program is associated to gender. Notice that in this pair of probabilities, the given part needs to change, in this occasion from female to male, and the other part needs to stay the same, business economy and business economy. This is the structure of the test for independence. The given part changes, B and B complement, and the other part stays the same, A and A. The probability of business economy given female is 0.070. The probability of business economy given male is 0.084. Obviously, this second probability is bigger, so men are more likely to study business economy than women. We can quantify how much more. If we divide the big number by the small, we get how many times the big number is as big as the small. This is 1.20. So we can answer question E very precisely. No, business economy is not independent of gender, it is associated to gender. Men are 1.2 times as likely as women to study business economy. Alternatively, you can speak in terms of percent more. What exceeds 1 here is the percent more likely. So you can say it in this way if you prefer. Men are 20% more likely than women to enroll business economy. The most common error in a procedure like this is comparing these two probabilities. If you don't change the given part, the comparison is meaningless because it might be biased by the proportions in the whole sample or the population. With a pair like this, we can conclude that there are more men than women in business economy, but maybe there are more men than women in all the programs because maybe there are more men than women in the total in the college. Remember the idea, probability of y as a function of x, so the x is given and the values of x must change. Question F. Is graphic design independent of gender? We do the same. The probability of graphic design given female is 0.017. The probability of graphic design given male is 0.017. These two probabilities are the same, so the answer is yes, graphic design is independent of gender. Men are as likely as women to enroll graphic design. This is an example in which we don't have association. There is a comment though, these two probabilities are the same when we consider 3 decimals. If we consider more and more decimals, one will appear that is different. So when do we consider the difference to be negligible? Some authors suggest that we can disregard a difference between two probabilities if the big one is less than 5% bigger than the small one. In other words, if we get less than 1.05 when we divide the big by the small. In this case, if we use 4 decimals, the probability of graphic design given female is 0.0169, and the probability of graphic design given male is 0.0167. So we could say that women are 1.2% more likely than men to enroll graphic design. But this difference is so small that usually we consider it negligible and we just say that graphic design is independent of gender. I want you to practice by doing the same analysis with the other programs. You will corroborate what is already clear, that the answer to the original question is, in this college, gender and program are not independent, they are associated. Women are more likely to enroll some programs and men are more likely to enroll some other programs, even when we saw that one particular program is independent of gender. Question G. Can we generalize the conclusion beyond our sample? We saw this in chapter 1. Since the sample is not random, we cannot generalize the conclusion. Whatever we conclude here about gender and programs is valid only for this college, or more precisely, for the students included in the contingency table. It is understood, though, that the table included all the population of students in the college. Even if the sample was random, inferring about the whole population would not be as direct as we did here. In chapters 7 through 11, we will see the challenges of such generalizations and how to proceed.